A spacecraft the size of a postage stamp could reach another star in your lifetime. This is the core promise of laser sailing, a radical new method of propulsion that could redefine our place in the cosmos. By the end of this journey, you will understand how beams of light might propel humanity to the stars within mere decades. We will uncover the extreme engineering of a gram-scale probe and confront the staggering challenge of guiding it across 4.37 light-years of empty space. What does it truly take to leave our solar system behind? That barrier of time is what has kept the stars locked away. Think about it for a moment. With the very best engines we have today, a mission to our nearest stellar neighbor would not reach its destination for longer than all of recorded human history. Generations would be born and pass away aboard a ship that had become its own isolated world, its original purpose a fading myth. This timescale isn't just an inconvenience, it's a definitive wall. It means that with conventional rocketry, interstellar travel is not merely difficult, it is functionally impossible for a civilization like ours. We would be sending a monument, not a mission. So the dream demands we ask a different question entirely. What if the spacecraft didn't have to carry its own fuel? What if, instead of a roaring chemical furnace, the engine remained right here at home, and the vehicle was simply pushed gently and relentlessly by an external force? This is the profound shift in thinking that cracks the interstellar code. It moves us from the paradigm of the ox cart, hauling all its supplies for the long journey, to that of a sailboat, which harnesses an energy that is already everywhere. In the emptiness of space, that ubiquitous energy is light. The pressure of photons, tiny particles of light, though imperceptible to us on Earth, becomes a continuous, fuel-free push in the vacuum. A spacecraft equipped with a vast, ultra-thin reflective sail could, in theory, catch this beam and accelerate to velocities previously reserved for subatomic particles. It transforms a science fiction image, a gleaming silver sail billowing in the solar wind, into a serious engineering blueprint, the first practical step toward turning a millennia-old dream into a tangible destination. That tiny push is the secret. It feels like nothing because on our scale it is almost nothing. A beam of sunshine on your hand exerts less force than the weight of a single grain of sand. But in the frictionless realm of space, where there is nothing to slow you down, almost nothing adds up. A constant, whisper-soft nudge, applied hour after hour, day after day, year after year, begins to compound into something extraordinary. This is the physics of patience, where acceleration is measured not in roaring g-forces but in the relentless accumulation of speed. The key is that light does not just deliver energy, it delivers momentum. When a photon, a particle of light, bounces off a perfectly reflective surface, it gives that surface a double kick, once when it arrives and again when it leaves. It is like catching a stream of rubber balls and throwing them back. With each catch and throw, your hand is pushed backward. For a spacecraft, that backward push is actually a forward acceleration. The mathematics governing this are elegant and direct. The force you get is equal to twice the power of the light beam, divided by the universal speed limit, the speed of light. This equation reveals the entire challenge and the entire opportunity in one clean line. To generate any useful force from something moving at 299,792,458 meters per second, you need one of two things, or better yet, a combination of both. You need a light source of almost unimaginable power, or you need a spacecraft of almost unimaginable lightness. Breakthrough Starshot looks at that equation and decides not to choose. It pursues the ultimate combination, aiming a titanic laser at a probe barely heavier than a paperclip. This transforms a subtle physical curiosity into a formidable engine. It means we are not waiting for a gentle solar breeze to slowly fill a vast sail over centuries. We are building a concentrated hurricane of light in a specific direction, a focused push so potent it could, in theory, take a nanocraft from 0 to a fifth the speed of light in mere minutes. Grasping this momentum exchange is the essential leap, the moment you realize the cosmos has been offering us this propulsion method all along, hidden in the very fabric of starlight. This vision has a name and a formidable champion. In 2016, a program called Breakthrough Starshot was unveiled to the world, funded by a $100 million commitment from investor Yuri Milner. Its stated goal was as simple as it was audacious: to prove that a flyby mission to Alpha Centauri could be achievable within a single human lifetime. This was not a plan to build a Starship. It was a coordinated global effort to solve, piece by piece, the fundamental physics and engineering puzzles that stand between our solar system and the next. The scale of the proposed system reads like a catalogue of extremes. Imagine a mothership, a silent bus in high Earth orbit. Its cargo bay opens not to release one sophisticated probe, but to deploy a swarm, thousands of them. Each one is a nanocraft, a silent flake of technology no larger than a postage stamp and weighing barely a gram. For a moment they drift, then, from the surface of our planet, a new kind of sunrise is engineered. A vast array of lasers, a forest of beams spread across a kilometer or more, all synchronize their light into a single, coherent torrent of power. This is not a continuous beam for years on end, but a focused pulse of energy lasting only minutes. In that brief, violent interval, the laser array pours a gigawatt of power, the output of a large nuclear reactor, onto the reflective sail of a single nanocraft. The sail, only a few hundred atoms thick, billows not with wind but with pure radiation pressure. In those few minutes, the tiny craft is not gently pushed but violently hurled, accelerating at tens of thousands of times the force of Earth's gravity until it is receding at 1/5 the speed of light. The mothership repeats this process, beaming each successive probe toward the same celestial target. The travel time plummets from tens of millennia to just over 20 years. This is the staggering arithmetic of Starshot, where the sacrifice of mass and the concentration of power rewrite the rules of the possible. It is a plan that acknowledges the true nature of the challenge, recognizing that reaching another star is not a single invention, but a symphony of 10,000 innovations played in perfect, unprecedented harmony. That symphony of 10,000 innovations begins with its smallest and most critical note, the StarChip itself. This is the soul of the mission, a fully functional spacecraft engineered to weigh less than a single raisin. To grasp the sheer audacity of this, picture your smartphone. Now, imagine stripping it down to its absolute essence, the core systems for seeing, thinking, and speaking, and then shrinking that entire package onto a silicon wafer the size of a postage stamp. This is not just miniaturization, it is a complete reimagining of what a spacecraft can be. Every single component must be reinvented from first principles. The camera cannot be a bulky lens and sensor array. It might be a flat, nanostructured surface that bends light in revolutionary ways. The processor cannot guzzle power. It must be an ultra-efficient speck of silicon, perhaps only a few millimeters across, running specialized software. Even the power source is a profound puzzle, a tiny battery or capacitor that must survive decades of deep cold and then burst to life for a fleeting encounter, all while being charged by a distant, fading laser beam. And then it must speak. The antenna for sending data back across 4 light-years cannot be a large dish. It will likely be the sail itself, using its reflective surface to modulate a laser signal back toward Earth. Each of these systems is a frontier of science, pushing nanotechnology and materials science into realms we are only beginning to map, but the challenges go beyond mere size. This silent flake of technology must endure a journey more punishing than any we have ever designed for. It will be bombarded by cosmic radiation, energetic particles that can scramble delicate electronics. The temperature will plummet to just a few degrees above absolute zero, a cold so profound it can make materials brittle and fail. And it will be racing through space at a fifth the speed of light, where a collision with a mote of dust, a micrometeoroid smaller than a grain of sand, would deliver the explosive energy of a high-powered rifle shot. Hardening the StarChip against these threats means building it from new, resilient materials, perhaps layering it in protective coatings only atoms thick, and designing self-healing circuitry. Guidance is another monumental puzzle. With no fuel for traditional thrusters, how does such a tiny craft steer or stabilize itself? One elegant solution uses the pressure of light itself. By carefully adjusting the reflectivity of different sections of its sail, or by using tiny, laser-powered photon thrusters etched onto its edges, the nanocraft could make minute course corrections, using the very beam that propelled it to also guide it. And overseeing all of this must be a sliver of artificial intelligence, an onboard manager of extreme scarcity. This AI would have to monitor systems, prioritize data collection during the brief, high-speed flyby of Alpha Centauri, and decide what precious information to beam home. It is a testament to human ingenuity that we are not just dreaming of such a device, but actively blueprinting its components, forcing the impossible to become merely a matter of engineering. Yet this microscopic brain and heart would be utterly powerless without its wings. The light sail is not just a component, it is the entire propulsion system, a silent engine woven from atoms and light. To function, it must achieve a near-impossible trifecta. It must be almost perfectly reflective to catch every possible photon of momentum from the laser. It must be astonishingly thin and light, because every extra microgram is a penalty in final speed, and it must be incredibly strong to survive being blasted by a gigawatt beam without instantly vaporizing into a cloud of plasma. The materials that could meet these demands sound like they are from a science fiction catalog. Engineers are looking at ultra-thin sheets of graphene, a lattice of carbon only one atom thick, yet stronger than steel. They are investigating molybdenum disulfide, another two-dimensional wonder material with unique optical properties. The goal is a sail just a few hundred atoms thick, a fabric so fine it would seem to be made of solidified light itself. But reflectivity and strength are only the beginning. The sail's shape is a physics puzzle of its own. When that titanic laser pulse hits, the pressure will be immense, trying to crumple the delicate film or send it into a wild, uncontrollable spin. To remain stable, the sail cannot be a simple flat sheet. Some designs propose giving it a slight curvature, like a shallow dish, to naturally focus the pressure toward its center and keep it aligned. Others imagine spinning the entire craft, using gyroscopic forces to act like a spinning top, maintaining a steady orientation across light years. There is even a fascinating idea to move beyond simple reflection altogether. Instead of a mirrored surface, a diffractive sail would be etched with microscopic patterns, like a complex grating. This would allow it to bend the incoming laser light in precise ways, offering much finer control over steering and stability, turning the sail from a passive reflector into an active optical instrument. The challenge of heat is perhaps the most severe. Even with near-perfect reflectivity, a tiny fraction of that colossal laser energy will be absorbed as heat. For a structure only atoms thick, this is like holding a magnifying glass over a snowflake. Managing this thermal load requires ingenious design, perhaps weaving in channels only nanometers wide to radiate heat away, or choosing materials that can withstand phenomenal temperatures without melting. Crafting this perfect interstellar kite is a dance at the limits of material science, where the laws of optics, thermodynamics, and structural integrity meet. It is the ultimate expression of building not with bulk, but with precision, where saving a single atom of mass can mean shaving years off the journey to the stars. But even the most perfect sail is useless without its engine. The true powerhouse of this mission would never leave the ground. It is a laser array of staggering ambition, a planetary-scale flashlight designed to push a speck across the cosmos. This is not a single device you could point at the sky. It is a forest of beams, thousands of individual lasers spread across perhaps a square kilometer of high desert, all synchronized to act as one coherent torrent of light. Their combined power output would be measured in gigawatts, rivaling the total electricity production of a large city or a nuclear power plant, but focused into a beam only a few meters wide. The scale of this infrastructure is difficult to overstate. It is less a scientific instrument and more a monumental piece of civil engineering, a new kind of lighthouse whose purpose is not to warn but to launch. Choosing where to build such a thing is a science in itself. The ideal site needs an atmosphere that is exceptionally calm, dry, and clear to minimize the light's distortion. A leading candidate is a place like the Atacama Desert in Chile, high on a mountain plateau where the air is thin and stable, and the skies are among the clearest on Earth. Even here, the atmosphere is a turbulent, shimmering lens. Air currents, temperature changes, and moisture all bend and scatter the laser light, causing the beam to blur and wander. If left uncorrected, this atmospheric turbulence would smear that pinpoint gigawatt beam across the sky, its energy diffusing into uselessness long before it reached the sail. To defeat this, the array would employ a technology called adaptive optics. It works by using a bright guide star, either a real star or a laser beam projected into the upper atmosphere, to measure the distortion in real time. A computer then analyzes this distortion and commands hundreds of tiny actuators to deform a flexible mirror in the laser's path, thousands of times per second. This mirror pre-corrects the beam, bending it in the exact opposite way the atmosphere will, so that by the time it passes through the turbulent air, it emerges as a sharp, focused column of light. It is like trying to throw a perfect spear through a raging river by calculating the water's currents and adjusting your aim before you even let go. The precision required does not end there. As the nanocraft accelerates, it moves across the sky with breathtaking speed. The entire laser array, this kilometer-wide installation, must track its target with the accuracy of a sniper keeping crosshairs on a speeding bullet, but from thousands of kilometers away. Every individual laser emitter must adjust its phase in perfect harmony with all the others to keep the combined beam locked onto a sail that is, by then, just a shimmering dot receding into the black. This orchestration of light, mechanics, and computation has no precedent. It represents a leap in optical engineering comparable to the jump from a candle to a searchlight, and then demanding that searchlight perform with the precision of a surgical laser. Building and operating this system is a colossal undertaking that stretches our capabilities in energy production, optical fabrication, and supercomputing control. It forces us to ask not just if we can reach the stars, but if we can master our own planet's veil of air to create a doorway of pure light through it. Those final, critical minutes begin in utter silence. The nanocraft floats in the blackness, its sail a perfect gossamer mirror angled toward the distant blue dot of home. On the ground, across a square kilometer of desert, a forest of lasers hums with stored energy. There is no countdown broadcast into space, no dramatic ignition sequence. There is only the sudden, coordinated unleashing of light. In an instant, a torrent of photons with the collective power of a nuclear reactor converges into a single, coherent beam and punches upward through the atmosphere. For the nanocraft, the universe transforms. The gentle pressure of sunlight it felt moments before is replaced by a force of biblical magnitude. It is not pushed, it is hammered. The acceleration slams into the tiny vehicle, reaching tens of thousands of times the force of Earth's gravity. To survive this, the entire structure must be engineered like a vault, yet weigh less than a gram. Every atom of its frame, every circuit etched into its silicon heart, must be designed to withstand a pressure that would instantly crush a battleship into a speck. This is the violent, necessary birth of a starship. Within those few minutes, the silent speck must be hurled from a standstill to a velocity so great it defies everyday understanding, 60,000 kilometers every single second. It is a transition so rapid that if the craft had a clock, time itself would begin to slow down relative to us almost immediately, a real effect of relativity kicking in at these fantastic speeds. The peril of this phase cannot be overstated. It is a razor's edge between triumph and instantaneous, vaporizing failure. The sail must remain perfectly reflective, for even absorbing a tiny fraction more of that colossal energy than calculated would superheat its delicate membrane, turning it into a brief, brilliant plasma. The beam must remain perfectly focused and centered. A slight wobble or misalignment would rip the sail or send the craft into a catastrophic tumble. And the atmosphere, even with adaptive optics correcting for its shimmer, is a turbulent ocean of air. An unexpected pocket of turbulence could scatter the beam at the worst possible moment, diffusing its push into uselessness. For the engineers watching, these minutes represent a terrifying binary. There are no partial successes, no graceful degradations. Either the nanocraft survives intact, now a relativistic bullet on a 20-year journey, or it is simply gone, transformed into a fleeting spark of light and data lost forever in the noise. Every innovation, every atom-thick layer of material, every line of stabilizing code exists for this singular trial by photon fire. It is the ultimate test of a concept, where the dream of the stars is either forged in light or extinguished by it. The hammer blow of acceleration ends as suddenly as it began. The laser beam, having done its work, falls away, its light now far too weak to be of any use. What remains is a profound and absolute silence. For the next 20 years, the nanocraft will not be an active ship, but a silent bullet, coasting on pure momentum through the interstellar dark. Its velocity is now a constant, a breathtaking 1/5 the speed of light, a number so large it loses meaning. At this pace, it would circle the entire Earth in less than a single second. Yet across the cosmic distances to Alpha Centauri, that incredible speed translates to a journey measured in decades. This is the long cruise, a phase defined not by action, but by endurance. The craft becomes a time capsule of technology, a functional artifact that must outlast the memory of its own launch for a generation. Its primary mission now is not to travel, but simply to survive. The environment it passes through is anything but empty. Interstellar space is a thin, frigid soup of radiation and microscopic debris. Cosmic rays, high-energy particles flung from distant supernova and black holes, will constantly pepper the tiny craft. These particles can pierce solid metal, and for a chip of silicon only atoms thick, they pose a constant threat of flipping a critical bit of memory or damaging a delicate circuit. Without the protective blanket of Earth's magnetic field and atmosphere, the nanocraft is naked to this barrage. Then there is the dust. At these velocities, a collision with a microscopic grain of matter, no larger than a particle of smoke, would be catastrophic. The energy released would be equivalent to a high explosive, easily vaporizing the entire probe. The statistics of such an impact are a terrifying game of chance played across light years. Mission planners can only hope the path is clear and perhaps design the craft with some redundancy, spreading its critical systems across the wafer so a single strike does not mean total loss. And permeating everything is the cold. The temperature will stabilize just a few degrees above absolute zero, the point where all molecular motion theoretically stops. This profound cold is a double-edged sword. It helps preserve the craft by slowing down any potential chemical degradation, but it also threatens to make materials brittle and snap, and it saps the life from the tiny batteries and electronics. To meet these challenges, the nanocraft will almost certainly enter a state of deep hibernation. Nearly all of its systems will power down into an ultra-low energy mode, a kind of technological cryosleep. Only the most essential monitors, perhaps a simple cosmic ray detector or a timer, will remain barely awake, ticking off the years. Its main computer and sensors will lie dormant, conserving every joule of energy stored in its microscopic power cell for the few precious hours of the Alpha Centauri flyby. This hibernation is an act of profound patience. It requires components that can not only withstand the harsh environment, but can also wake up perfectly on command after 20 years of silent, frozen darkness. It is a demand for reliability on a timescale that dwarfs most of our satellites. We are asking a gram of technology to remain flawlessly dormant for longer than the Voyager probes have been traveling, trusting that when the alarm finally rings at the edge of another star system, a tiny spark of human ingenuity will flicker back to life in the endless night. 20 years of silent coasting culminates in a final, frantic dash. The internal timer triggers and systems stir from their deep freeze. The nanocraft is now approaching the Alpha Centauri system at a staggering fraction of light speed, and its entire mission, decades in the making, will be decided in a matter of hours. This is not a leisurely orbital insertion. There is no fuel to slow down. The craft is a high-speed bullet, and its goal is a single, fleeting snapshot of another star system as it screams past. The precision required for this flyby is almost beyond comprehension. Missing the target by even a small margin would mean sailing uselessly through the interstellar void, its precious data lost forever. So how does a speck, launched from Earth a generation ago, possibly know where it is and where it needs to go? The answer rewrites the book on cosmic navigation. Within our solar system, probes use the planets as landmarks, bouncing radio signals off them and watching their positions against the background stars. But for the vast, empty stretch between stars, those familiar signposts vanish. The nanocraft is utterly alone, navigating a featureless ocean with no shore in sight. Its primary reference point becomes the very place it left behind. Engineers could send faint, carefully timed laser pulses from Earth toward the craft. By measuring the exact time it takes for those pulses to make the 4-year journey there and back, the nanocraft's onboard computer could calculate its distance and velocity with incredible accuracy. It is like echolocation on a galactic scale, using light instead of sound. Each pulse is a cosmic ping, a whisper from home saying, "You are here," but there is a backup system, one written in the stars themselves. Scattered across the galaxy are natural lighthouses called pulsars. These are the spinning cores of exploded stars, neutron stars that beam radiation with the metronomic regularity of atomic clocks. Each pulsar has a unique signature, a specific rhythm and position. By locking onto the signals from several known pulsars, the nanocraft could triangulate its position anywhere in the galaxy, creating a celestial GPS system built into the fabric of the universe. This navigation must be flawless from the very beginning. A steering error of just 1/10,000th of a degree at launch, a wobble smaller than the width of a human hair seen from a kilometer away, would grow over 4.37 light-years into a miss of millions of kilometers. To correct for this, the craft cannot rely on bulky thrusters. Instead, it might use its sail in a new way, by slightly changing the reflectivity of different segments of that atom-thin film. Perhaps with microscopic shutters, it could alter how the faint pressure of starlight pushes on it. This photon pressure, infinitesimal but constant, could provide just enough force for minute course adjustments over the decades, gently nudging the bullet back on target. The final approach is a ballet of autonomous decision-making. The onboard artificial intelligence, now fully awake, must process navigation data, identify the target stars, and command the craft to orient its instruments. It has one chance. As it plunges through the Alpha Centauri system, its tiny camera will snap a rapid-fire burst of images. Its spectrometers will analyze starlight filtered through any planetary atmospheres, and its dust detectors will map the debris in this alien realm. All of this precious data, the entire purpose of the 20-year voyage, must then be compressed and stored. But how does a postage stamp send a message home across that same unimaginable gulf? Our destination is a family of stars. Alpha Centauri, that bright point of light in our southern sky, is not one sun but three, bound together in a complex gravitational dance that has lasted for billions of years. The primary pair, Alpha Centauri A and B, are stars remarkably similar to our own Sun, locked in a slow, stately orbit around each other, their separation varying from roughly the distance of Saturn from our Sun to that of Pluto. This binary duo is the heart of the system, but the most famous member is the third, a faint, cool red dwarf called Proxima Centauri. It swings on a much wider, slower path thousands of times farther out, taking perhaps 500,000 years to complete a single loop around its brilliant siblings. It is around this dim, turbulent little star that our greatest interstellar hope currently orbits, a rocky world named Proxima b, nestled within its star's habitable zone where temperatures could allow for liquid water. This is the most likely target for our nanocraft's fleeting visit, a world that, for all we know, could be the first Earth-like planet we ever see up close. But reaching it means threading a needle through a celestial maze. The gravitational fields of three stars create a shifting web of forces, a dynamic environment where a straightforward path is impossible. Mission planners must calculate a trajectory that uses the gravity of the larger stars not as an obstacle, but as a tool, a slingshot to bend the nanocraft's path precisely toward Proxima and its enigmatic planet. This is interplanetary billiards played on a stellar scale, where the cue ball is moving at 1/5 the speed of light and you only get one shot. The flyby itself would be a blur of frantic activity. After 20 years of silence, the nanocraft systems would erupt into a controlled frenzy for a few short hours. Its tiny camera, likely a revolutionary flat lens, would begin snapping thousands of images. We would not see continents or oceans from such a high-speed pass, but we would get our first ever resolved picture of another planet beyond our solar system, even if it is just a pixelated dot that grows and then shrinks in the frame. More importantly, spectrometers would analyze the light filtering through Proxima b's atmosphere, if it has one, hunting for the chemical fingerprints of gases like oxygen, methane, or carbon dioxide, potential signs of a living world. Dust detectors would map the debris in the system, and magnetometers would sense the interactions between the star's fierce flares and the planet. Every instrument, every sensor on that gram-scale wafer would be collecting data at a furious pace, knowing this moment will never come again. In a matter of hours, the tiny craft would complete its primary mission, leaving the Alpha Centauri system behind as swiftly as it arrived, now carrying within its silicon memory the first direct portrait of another Earth, a treasure it must now find a way to send home across the light years. The flyby is a desperate, beautiful sprint. After 2 decades of frozen slumber, the nanocraft's microscopic brain jolts awake, its systems flooding with the last reserves of power. It has mere hours before it screams past its target forever. There is no time for contemplation, only for a frantic, orchestrated burst of observation. At 1/5 the speed of light, the entire Alpha Centauri system will unfold and vanish in less time than a single Earth day. Every instrument on that gram-scale wafer must perform perfectly. A revolutionary flat lens camera, perhaps no wider than a pencil lead, begins snapping a rapid-fire sequence. The images will not be postcard vistas. From such immense speed and distance, a planet like Proxima b would appear first as a single pixel, then a smudge of color, then a tiny crescent before receding again. Yet that pixelated dot would be a monumental first, our initial resolved image of another world orbiting another sun. Alongside the camera, a spectrometer the size of a grain of salt gets to work. It does not look for landscapes but for stories written in light. As starlight from Proxima filters through the planet's atmosphere, if one exists, specific wavelengths are absorbed by the gases present. The spectrometer captures this altered light, creating a chemical barcode. Scientists back on Earth would pore over that data, searching for the telltale lines of water vapor, methane, or even oxygen, potential biosignatures hinting at processes we associate with life. Meanwhile, a magnetometer thinner than a human hair measures the invisible magnetic fields, mapping how the star's fierce flares interact with the planetary environment, clues to whether a world there could be sheltered or scorched. This entire symphony of data collection is compressed into a digital whisper, a few precious gigabytes representing the sum of human curiosity about our nearest stellar neighbor. But then comes the mission's final and perhaps most daunting puzzle. How does a postage stamp with the power of a child's toy shout its findings across 4.37 light-years of emptiness? The answer is a feat of optical precision that defies belief. The nanocraft cannot carry a powerful radio transmitter that would require weight and energy far beyond its limits. Instead, it will use its only large structure, its light sail, as a cosmic mirror. A tiny, onboard laser, no more powerful than a standard presentation pointer, will fire its beam toward the sail. By minutely adjusting the sail's shape or reflectivity with microscopic actuators, the craft can encode the data into the laser light, modulating the beam like a high-speed Morse code. This faint, blinking signal is then reflected off the sail, which acts as a dish antenna, focusing it into a narrow beam aimed precisely back at our solar system. Think of it as using a pocket flashlight to send a signal from the coast of California to a specific window in a skyscraper in New York, but with the added complication that both the flashlight and the skyscraper are moving through space at different orbital speeds. The signal that finally reaches Earth after a 4-year journey through the void will be unimaginably weak, a few photons per second perhaps, buried in the cosmic radio noise. To catch this whisper, we would need a new generation of telescopes on Earth, vast arrays of receivers spread across continents, all listening in unison for that faint, rhythmic pulse from the stars. The fly by itself is over in a flash, a climax of decades of travel, but the patient work of listening, of sifting starlight for a message from a silent speck, becomes humanity's next great vigil. That faint, blinking signal faces a gauntlet of emptiness. The laser communicator on board the nanocraft is a marvel of miniaturization, perhaps powered by a speck of radioactive material no larger than a grain of salt, a microscopic nuclear battery designed to emit a steady trickle of power for decades. Or it might rely on a postage stamp-sized solar cell, recharging slowly from the distant light of Proxima Centauri. Its task is to take the precious flyby data and encode it into a beam of light, then aim that beam with impossible accuracy back toward a tiny, moving pale blue dot 4.37 light-years away. The scale of this challenge is humbling. The laser itself would be extraordinarily weak, comparable to a common laser pointer. Over interstellar distances, that tight beam still spreads out due to the fundamental laws of optics. By the time it reaches our solar system, the signal is not a coherent beam but a diffuse wash of photons, so faint that only a handful per second might strike a telescope's mirror. It is the equivalent of trying to spot a single candle flame flickering on the moon while standing on Earth during a cloudy night. To have any hope of detecting this interstellar whisper, we must build ears of unprecedented scale. Earth's future observatories, like the extremely large telescope with its 39-meter mirror, will be essential. But even that colossal eye might not be enough alone. The most promising solution is an array, a coordinated network of giant telescopes spread across the globe or even in space, all listening in unison for that specific, rhythmic pulse of photons. Their combined collecting area acts as a single, planet-sized receiver, sifting the constant radio noise of the cosmos for the one pattern that says, "I was here and I saw this." The slowness of the conversation is a profound lesson in cosmic patience. With such a weak signal, data cannot stream home in a rush. The transmission rate would be agonizingly slow, perhaps just a few bits of information every second. Sending a single, modest image from the flyby, a grainy picture of a new world, could take months or even years of continuous, flawless broadcasting. This transforms triumph into a protracted vigil. Success is not a dramatic moment of contact, but a gradual, painstaking reconstruction. Scientists would spend years collecting photons, bit by precious bit, assembling the message like a mosaic from the depths of space. A single corrupted segment, a burst of solar interference or an unlucky cosmic ray hit on the nanocraft's transmitter could wipe out a crucial piece of the puzzle forever. This communication challenge reframes the entire mission. It is not enough to reach another star, we must also invent a way to hear its story told in the faintest of whispers, a testament that some discoveries are measured not in kilometers per second, but in photons per year. Yet this whisper of data must first survive the crossing. The void between stars is a deceptively hazardous place, far from the perfect vacuum we might imagine. It is filled with a tenuous mist of hydrogen and helium gas, and more critically, microscopic dust. These are not pebbles or rocks, but motes of material finer than smoke, remnants of ancient stellar explosions and the building blocks of future worlds. For a craft moving at conventional speeds, they are harmless, but at 1/5 the speed of light, physics transforms them into weapons. A collision with a single dust particle just 1 micron wide, smaller than a red blood cell, would release energy on par with a high explosive bullet. The impact would not just damage the nanocraft, it would vaporize it in an instant, reducing 20 years of travel and a gram of human ingenuity to a fleeting puff of plasma. The sheer scale of space offers the only possible shield. The distances are so vast and the dust so sparse that the probability of a direct hit on a sail the size of a picnic blanket is statistically very low. But it is not zero. Mission architects cannot armor the probe. Adding even a thin layer of protective material would make it far too heavy to accelerate. So they place their faith in the numbers, betting that the emptiness will hold. This is why the mission concept calls for a fleet, not a single vessel. By launching thousands of identical nanocraft, the hope is that even if 99% are lost to random dust collisions, a handful will make it through. Each probe is a ticket in a cosmic lottery, its survival a matter of fortune as much as engineering. Alongside this sporadic threat of annihilation exists a slower, more insidious danger. The galaxy is awash in cosmic rays, atomic nuclei stripped of their electrons and accelerated to nearly the speed of light by distant supernova and black holes. These particles are smaller than dust but carry tremendous energy, and they arrive in a constant, silent sleet. For a human astronaut, they pose a long-term health risk. For a nanocraft's delicate, atom-scale electronics, they are a persistent menace. A single cosmic ray strike can flip a digital bit from a 1 to a 0, corrupting memory or issuing a faulty command. Over decades, this relentless bombardment can degrade circuits, slowly eroding the probe's ability to think, remember, and function. To endure this, the nanocraft systems must be radiation-hardened from the ground up. This means designing microchips with redundant pathways, using materials less susceptible to damage, and writing software that can detect and correct errors autonomously. It is a form of technological immunization, preparing the probe's microscopic brain for a decades-long bath in a sea of high-energy particles. The strategy, then, is a layered one, blending redundancy with resilience. Send a multitude to beat the odds of catastrophic dust collisions, and harden each one to withstand the slow decay of radiation. It is an acceptance that the journey itself is a filter, and that reaching another star may require us to let go of our instinct for perfect control, embracing instead the stark statistics of the cosmos. The silent decades of the journey are powered by a profound constraint. Every single operation, from the faintest sensor reading to the laser pulse sent home, must be fueled by an energy source smaller than a fingernail. This is not about building a better battery. It is about redefining the very meaning of power for a machine destined to outlive its creators. A conventional solar panel, even a small one, would be far too heavy and fragile. A chemical battery with enough capacity would weigh more than the entire craft. So engineers look to the extremes of physics for answers, turning to the quiet, relentless decay of atoms themselves. One leading candidate is a speck of americium-241, a radioactive isotope commonly found in household smoke detectors. Encased safely within the nanocraft's wafer-thin body, this tiny pellet emits a steady trickle of heat as its atoms slowly break down over decades. That heat, mere thousandths of a watt, is not wasted. It is funneled through a thermoelectric generator, a solid-state device with no moving parts that converts temperature differences directly into electricity. It is a nuclear battery, a whisper of power that could persist for 50 years or more, perfectly matched to the timescale of the mission. This creates a delicate energy economy where every microwatt is budgeted years in advance. The craft's artificial intelligence becomes an accountant of extreme scarcity. For over 99% of the voyage, it commands the probe into a state of deep hibernation. Almost every system shuts down completely. The camera is blind, the computer's thoughts are frozen, the laser is dark. Only the most rudimentary timer and a handful of radiation-hardened memory cells remain active, drawing less power than a wristwatch. In this suspended animation, the craft is little more than a silent stone coasting through the dark, its nuclear battery slowly replenishing a microscopic capacitor for the day it will need to awaken. Periodically, perhaps once a year, the timer triggers a brief check-in. For a few minutes, a trickle of power flows to the navigation system. The craft listens for the faint laser pings from Earth or scans for its pulsar landmarks, makes a minute course correction using its sail, and then slips back into the deep freeze. This cycle of sleep and fleeting awareness defines the decades, a rhythm of patience written in code. The final awakening as the craft approaches Alpha Centauri is a controlled power surge. Every stored joule from years of careful saving is unleashed. The camera warms up, the spectrometers calibrate, the main processor begins its rapid-fire calculations for the flyby. For a few precious hours, the postage stamp becomes a fully operational scientific observatory, burning through its life's savings of energy in one glorious, data-gathering blaze. Then, just as quickly, it must downshift again. The primary mission is over, but a new, even more frugal phase begins, the long transmission home. The laser communicator, drawing from the now depleted power reserves, can only operate in short, scheduled bursts, perhaps for a few minutes each day, slowly etching its message into the light beam over months or years. This relentless energy scarcity is the invisible architect of the entire mission. It dictates the cadence of discovery, forces the invention of unimaginably efficient electronics, and reminds us that to touch the stars, we must first learn to think small and to wait. This tiny electronic brain must be a master of scarcity and resilience. Every decision it makes, from a minor course tweak to prioritizing which scientific observation to capture, is a transaction paid for with precious microseconds of processing time and nanowatts of power. We are not talking about the sprawling, energy-hungry neural networks that power internet searches or generate art. This is a different class of intelligence altogether, one built for survival in the harshest environment imaginable. Think of it as the ultimate survivalist, programmed with a deep, immutable understanding of its mission, yet flexible enough to adapt when the universe throws it a curveball 4 light-years from home. Its primary duty is vigilance. For decades, it will monitor the craft's vital signs, checking for radiation damage, tracking power levels, and ensuring the delicate instruments remain in their deep freeze slumber. It is a silent guardian running on a trickle of current, its code etched into radiation-hardened memory that can withstand the constant barrage of cosmic rays. When the timer finally signals the approach to Alpha Centauri, this guardian must transform into a field commander. The flyby sequence is too fast and the communication delay too great for any instruction from Earth. By the time we see the craft has entered the system, its entire encounter would already be over. So the artificial intelligence must execute a complex ballet of observations autonomously. It will identify the target planets against the glare of their stars, orient the craft to point its instruments, and manage the frantic data collection. But what happens if a key sensor fails at the last moment, or if an unexpected dust cloud obscures the primary target? This is where true adaptability is required. The AI must be able to reassess its priorities in real time. Its programming would include a hierarchy of goals, a kind of scientific triage. Perhaps capturing a clear image of Proxima B's crescent is the top objective, but if that becomes impossible, it might automatically switch to gathering more atmospheric spectral data instead. It might even have the capacity to recognize an anomaly, something utterly unexpected, and choose to investigate it, deviating from the pre-planned script in pursuit of a genuine discovery. This level of autonomous decision-making is what separates a simple probe from an interstellar explorer. We are entrusting the entire purpose of a decades-long, multi-billion-dollar endeavor to a few milligrams of silicon and code, asking it to think for itself when we cannot. The success of the mission truly does hinge on creating not just a smart machine, but a responsible one, a fragment of human curiosity made durable enough to whisper back to us from the stars. The ambition of Starshot is measured not just in light years, but in ledger books. While the physics presents a formidable challenge, the economics introduce a barrier of a different magnitude, one grounded in the practical realities of our world. Constructing the laser array, that planetary-scale installation with its adaptive optics and power systems, carries a price tag that could easily reach tens of billions of dollars. This places it in the realm of history's grandest scientific undertakings, comparable to the International Space Station or the Large Hadron Collider. Such a sum is far beyond the capacity of any single private entity or even most individual nations. It demands a new model of global partnership, a consortium of governments, space agencies, and perhaps visionary philanthropists, all aligned behind a goal whose payoff lies a generation in the future. This collaboration raises profound and practical questions. How would such an alliance be governed? Who decides when to fire the beam, and crucially, who owns the priceless data streaming back from Alpha Centauri? The answers would set a precedent for how humanity, as a whole, explores the cosmos beyond our solar system. The financial hurdle extends beyond the laser on the ground. To deliver its payload, the mission relies on a mothership in orbit, a platform that must deploy thousands of nanocraft. This requires getting massive amounts of material into space reliably and affordably. The entire architecture depends on the continued evolution of commercial spaceflight, on launch costs falling low enough to make lofting such a swarm economically feasible. The project's proposed timeline, aiming for a launch within a few decades, is not just a countdown to a technological milestone. It is a race against a confluence of advancements that must all arrive in sync. Breakthroughs in laser efficiency, material science for the sails, and the miniaturization of the StarChip must progress in parallel with the growth of global space infrastructure, and perhaps most elusively, the sustained political and public will to fund a venture where success is measured by a whisper of data that may not return for half a century. This is the ultimate test of long-term thinking, asking our present civilization to invest deeply in a question whose answer will be heard by our children or grandchildren. It transforms the mission from a mere engineering problem into a mirror held up to our species, questioning whether we can plan and build on a timescale that truly matches the stars. But beyond the ledger books and laser arrays lies a quieter, deeper set of questions. A mission to another star is not merely a technical or financial endeavor, it is a philosophical act. For the first time, we would be deliberately placing an artifact of human intelligence into another stellar system, a physical extension of our curiosity that will outlast our civilization's current form. This simple act of sending a silent, gram-scale observer compels us to consider our place in the cosmos in a new and urgent way. Are we merely passive observers peering through telescopes from the safety of our cosmic shore? Or does the act of sending something, anything, across that gulf make us active participants in a broader interstellar community, even if that community is, for now, only imagined? The physicist and philosopher Anders Sandberg frames this as a fundamental expansion of human agency. It is a choice to reach out and touch, however gently, a place that has forever been a point of light. This transition from watching to interacting, even in this most minimal way, carries a weight of responsibility we are only beginning to articulate. One of the most immediate concerns is the concept of contamination. Our probes are meticulously clean, sterilized to prevent carrying even a single Earth microbe to another world. But a nanocraft, by its very design, cannot undergo the intense heat sterilization of a Mars rover. While the chance of a terrestrial organism surviving the decades of interstellar radiation and cold is vanishingly small, and a flyby mission poses far less risk than a lander, the principle remains. We are introducing something foreign into a pristine environment. It is a reminder that our curiosity must be paired with profound care, a commitment to preserving the natural state of other worlds for their own sake and for the sake of future science and perhaps for future life we have yet to meet. This leads to an even more profound contemplation. What if we find something? The mission is designed to detect chemical biosignatures, hints of processes that could be biological. A positive signal, even a tentative one, from our nearest stellar neighbor would shake our understanding of life in the universe to its core. Are we, as a species, emotionally and culturally prepared for such a discovery? It would transform Alpha Centauri from a distant target into a place, a world with its own story, one that might include something akin to ourselves or something utterly alien. The data would be geological and atmospheric, but its interpretation would be a human story, filtered through our hopes, our fears, and our limited understanding. There are no easy answers to these questions, and they will not be solved by engineers or laser physicists alone. They require the insights of ethicists, artists, historians, and every one of us. As we stand on the threshold of building the tools to reach the stars, we must also cultivate the wisdom to understand what it means to send them. This silent, speeding postage stamp is more than a probe. It is a mirror, reflecting back at us who we are and who we aspire to be as we prepare to whisper our first hello into the cosmic dark. That single, pixelated image would rewrite our astronomy textbooks. For centuries, planets beyond our sun have been points of data, graphs of light curves and spectral lines inferred from unimaginable distances. A successful Starshot flyby would transform that abstract data into a place. The first close-up image of an exoplanet, even a grainy crescent captured at tremendous speed, would be a revelation. We would not see continents, but we might discern the contrast between land and ocean, the swirling patterns of cloud cover, or the stark outline of a mountain range silhouetted against the star's glow. This visual ground truth would tell us if Proxima b is a barren rock, a global water world, or a dynamic planet with weather systems and geology. It would move the concept of another world from the realm of mathematical probability into tangible reality, a landscape hanging in the void of another sun. The true scientific treasure, however, lies in the light we cannot see. As the nanocraft streaks past, its onboard spectrometer would perform a masterstroke of remote sensing. It would capture the starlight from Proxima Centauri as it filters through the thin veil of the planet's atmosphere, if one exists. Each gas in that atmosphere leaves a unique fingerprint, absorbing specific colors of light. By decoding this spectral barcode, scientists could read the chemical composition of an alien sky from 4 light-years away. The hunt would be for biosignatures, combinations of gases that are difficult to explain through geology alone. A significant abundance of oxygen alongside methane, for example, would be a tantalizing hint, as on Earth these gases react quickly and their coexistence suggests a continuous source like life. Finding water vapor would speak to a world with an active hydrological cycle. Even the absence of an atmosphere would be a profound discovery, telling us about the harsh reality of planets orbiting volatile red dwarf stars. This data would provide our first direct answer to one of humanity's oldest questions: are we alone in the universe, even if that answer is a complex and cautious maybe? Beyond the planet itself, the journey is the experiment. For the first time, we would have a probe traveling through the interstellar medium, the thin soup of gas and dust between stars at relativistic speeds. The nanocraft's instruments could directly sample this material, measuring its density, composition, and magnetic fields in regions we have only been able to observe from afar. This is like switching from studying the ocean by looking at its surface from a satellite to actually dipping a cup into the water and tasting it. Each microscopic dust grain it analyzes, each measurement of the galactic magnetic field, would be a new data point in our map of the local cosmos. We would learn about the environment that future, larger starships might one day traverse, understanding the hazards and the resources that lie in the great dark between suns. Ultimately, this mission is about more than a single star system. It is about opening a new window on the universe itself. Every piece of data returned would serve as a calibration point, a reality check for all our theories about how planetary systems form and evolve. Our current models are built from observations within our own solar system and the indirect glimpses of distant exoplanets. Starshot would give us a detailed, close-up look at another, entirely different system, one with multiple stars and a different type of sun. Does our solar system represent the common template, or is it an oddity? Are Earth-like worlds rare or plentiful around small, faint stars? The answers would reshape our understanding of our own cosmic neighborhood and our place within it. The mission transforms from a daring sprint to Alpha Centauri into a foundational act of cosmic science, sending back not just pictures, but the first pieces of a new reality, one where the stars are no longer just points of light, but destinations filled with mystery and promise. The quest to reach the stars is already reshaping our world. While the grand vision of a nanocraft sailing to Alpha Centauri captures the imagination, the intense research required to make it possible is not happening in a vacuum. Every engineering problem solved for that 20-year journey has the potential to spin off into technologies that touch our daily lives, creating a cascade of innovation here on Earth long before the first laser is ever fired into the void. This is the hidden heartbeat of such an ambitious project, where the pursuit of the extraordinary relentlessly improves the ordinary. Consider the challenge of communicating with a speck of dust 4 light-years away. To achieve that, scientists are pushing laser communications to its absolute limits, developing systems that can encode vast amounts of data into a beam of light and transmit it with pinpoint accuracy over staggering distances. The same principles scaled down could revolutionize how we connect here on the ground. Imagine a future where ultra-fast, secure internet networks are beamed directly between towers or even to individual homes, using focused light instead of crowded radio waves. This could bring gigabit-speed broadband to remote areas, create unhackable communication links for finance and government, and alleviate the congested spectrum that our wireless world increasingly relies upon. The technology to whisper across the galaxy might first give us a better way to stream a movie or join a video call. Then there are the materials to build a sail that is strong enough, light enough, and reflective enough to survive a gigawatt laser. Researchers are inventing entirely new substances. They are engineering metamaterials, fabrics with structures engineered at the nanoscale to manipulate light in ways nature never intended. These are not just for interstellar sails. Once mastered, such materials could lead to a new generation of ultra-efficient solar panels that capture a wider spectrum of sunlight, or to lenses for cameras and medical imaging devices that are perfectly flat, eliminating distortion and allowing for scanners that see inside the human body with unprecedented clarity. The quest for the perfect atom-thin mirror might one day help doctors detect illnesses earlier and with greater precision. The extreme miniaturization demanded by the StarChip is another fountain of innovation. Packing a functional spacecraft into a gram forces engineers to reinvent sensors, processors, and power systems at a microscopic scale. These advances will inevitably trickle down. We could see medical implants that are smaller, smarter, and longer lasting, monitoring health from within the body with minimal intrusion. Consumer electronics could become even more powerful and energy efficient, with sensors in everything from phones to home appliances becoming vastly more capable. The tiny environmental sensors developed for the craft's journey could be deployed by the millions across our planet, creating a hyper-detailed, real-time map of atmospheric health, pollution levels, and climate indicators. Even the monumental laser array itself drives progress. The need for a coherent, high-power, and precisely controlled beam pushes the entire field of photonics forward. More efficient and powerful lasers have countless applications, from advanced manufacturing and cutting-edge surgery to new forms of energy research. The adaptive optics systems, designed to see through atmospheric turbulence to aim at a distant sail, can be turned back toward the heavens, giving our ground-based telescopes crystal-clear views of the cosmos, or they can be adapted to improve long-distance free space communication on Earth. In this way, the journey and the destination are deeply intertwined. The technological pathway to the stars is paved with breakthroughs that heal, connect, and enlighten our own world. This means that investing in such a profound dream is not a diversion of resources, but a powerful engine for terrestrial progress. The greatest legacy of an interstellar mission may not be the first image of Proxima b, but the invisible wave of innovation it sends rolling through our laboratories, hospitals, and homes, proving that by looking intently toward the horizon, we inevitably improve the ground beneath our feet. That optimistic timeline rests on a breathtaking acceleration of human ingenuity. A launch within a few decades is not a prediction, it is a provocation. It demands that solutions to a dozen separate, monumental challenges, the perfect sail, the planetary laser, the whispering communicator, all converge within the next 10 to 20 years. Only then could another decade be spent on the actual construction and testing of a system of unprecedented scale. History offers a sobering counterpoint. Grand visions in space exploration, from the Apollo program to the James Webb Space Telescope, have a consistent habit of arriving later and costing more than the most hopeful initial estimates. The complexity always reveals hidden layers, and the universe never fails to present new puzzles. So, is the timeline realistic? It is perhaps the wrong question. The more useful inquiry is what the timeline does. By setting a goal that seems just within reach of a working lifetime, it acts as a powerful social and technological catalyst. It compresses a century of speculative research into a single generation's focused sprint. Instead of scattered academic papers, it creates a global engineering roadmap. Teams around the world now have a specific, staggering benchmark against which to measure their prototypes. A new material is not just interesting, it is evaluated against the need to reflect a gigawatt laser. A tiny laser is not just novel, it is tested for its ability to signal across light years. This deadline, however aspirational, creates a forcing function for exponential progress. The fields it relies on, photonics and nanotechnology, are indeed advancing at a staggering pace. The computer chip that once filled a room now fits in your palm, a revolution that unfolded in decades, not centuries. The timeline dares us to believe a similar revolution in interstellar capability is possible. It transforms the mission from a distant dream for posterity into a tangible project for the people alive today, inviting engineers, scientists, and dreamers to pick up a piece of the puzzle and make it real within their own careers. This shift in psychology may be its most important contribution, proving that the most audacious deadlines are sometimes the only ones that can truly mobilize us to rewrite the possible. Laser sailing is not the only idea on the drawing board. Throughout the 20th century, visionaries proposed other, equally radical methods to breach the interstellar gulf. One of the most famous is nuclear pulse propulsion, a concept known as Project Orion. Its principle was shockingly direct, detonating atomic bombs behind a massive, shielded spacecraft. Each explosion would slam against a giant pusher plate, propelling the ship forward in a series of titanic, controlled jolts. This brute force approach could, in theory, accelerate vessels the size of small cities to a few % of light speed, enabling missions to the outer solar system and perhaps to nearby stars over centuries. It was a design of staggering scale, born in an era that believed any problem could be solved with enough raw power. While the physics was sound, the political and environmental realities of launching such a ship from Earth proved insurmountable, leaving it as a haunting monument to a different path not taken. Fusion rockets represent a more refined, though still elusive, alternative. Instead of uncontrolled explosions, they would harness the same process that powers the sun, fusing hydrogen isotopes to create a superheated plasma and directing it out a magnetic nozzle for thrust. A functioning fusion drive would be a game changer, offering high thrust and efficient fuel use for voyages throughout our solar system. For interstellar travel, however, it faces a fundamental limitation of mass. To reach even a tenth of light speed, a fusion rocket would need to carry a prohibitive amount of fuel, most of which would be spent accelerating that very fuel itself. This tyranny of the rocket equation makes it better suited for slower, generational ships or as a potential braking system at a destination, rather than as the primary engine for a swift sprint to the stars. Then there are the ideas that dwell at the very edge of known physics, concepts that promise shortcuts through the fabric of space itself. The theoretical Alcubierre warp drive, inspired by the stretching of spacetime described by Einstein's equations, proposes contracting space in front of a ship and expanding it behind, effectively creating a bubble that moves faster than light without the vessel itself breaking any local speed limits. It is a beautiful mathematical possibility, but one that requires forms of matter with negative energy density, substances we have no evidence can exist or be manufactured. Similarly, devices like the controversial M-Drive, which claim to produce thrust without expelling any propellant, have failed to demonstrate their effect under rigorous, controlled testing. They remain outside the consensus of established physics, fascinating curiosities but not engineering blueprints. This landscape of alternatives is crucial for understanding why laser sailing has captured such serious attention. It does not require new physics or magical materials. Every principle it relies upon the momentum of photons, the reflectivity of materials, the coherence of laser light, is grounded in equations we have tested and trusted for over a century. The challenge is not discovering a new law of nature, but mastering our current ones with an intensity we have never before attempted. It is a matter of scale, precision, and integration, of pushing materials science, optics, and nanotechnology to their absolute limits. When compared to the daunting unknowns of warp fields or the colossal engineering of Orion, the path of Starshot appears almost straightforward. It presents a clear, if extraordinarily difficult, engineering pathway to relativistic speeds within the framework of our current scientific understanding. This is why, for now, a beam of light pushing a silent sail represents our most plausible, near-term ticket to another star. It is a testament to a profound truth that sometimes the most revolutionary journeys begin not by breaking the rules, but by following them further than anyone ever dared. A ground-based laser is a monumental challenge, but it might also be a necessary compromise. For all its difficulties with atmospheric turbulence and colossal infrastructure, building here on Earth leverages our greatest strengths, our ability to construct massive projects with relative ease and to tap into vast power grids. It represents a first step, a way to prove the core concept of laser sailing without first having to conquer the even more daunting task of building in the void. Yet for many scientists, the ground is merely a training ground. The ultimate expression of this technology, the key to unlocking the entire galaxy, would have to leave our planet behind. The logical, perhaps inevitable, next step is to move the laser itself into space. Imagine that forest of beam emitters not spread across a desert valley, but assembled into a vast, silent array floating in the perpetual sunlight of a stable orbital point, like the Lagrange points where the gravitational pulls of Earth and the Sun balance. Here, there is no atmosphere to distort the beam, no shimmering air, no clouds, no turbulent weather to scatter that precious, focused column of photons. A space-based laser could maintain its razor-sharp focus across vastly greater distances, pushing sails with even greater efficiency. This single advantage transforms the mission's potential. A cleaner, more stable beam means you could achieve the same incredible speeds with less power, or push slightly heavier payloads, perhaps even small clusters of nanocraft acting together. More profoundly, it redefines the destination menu. A ground-based system straining against Earth's atmospheric veil might be practically limited to our very closest stellar neighbors like Alpha Centauri. But a pristine beam from a space-based array could realistically target stars farther out, potentially reaching a dozen or more Sun-like stars within a 20-light-year radius. Our celestial backyard would suddenly become a neighborhood of reachable destinations. The engineering leap to a space-based laser, however, is of a different order of magnitude. We are no longer talking about building on a remote mountaintop, but about constructing what would be the largest, most complex structure ever put into space. This array, likely kilometers across, would have to be assembled piece by piece in orbit, a process requiring decades of autonomous robotic construction or a continuous human presence in space. Its power needs would be gargantuan. It could not plug into a planetary grid. It would need to generate its own electricity, most likely from vast, fragile wings of solar panels spanning many square kilometers, or from a revolutionary space-based nuclear reactor. Every component would need to withstand the relentless hail of solar radiation and micrometeoroids for centuries. the cost would be astronomical, dwarfing even the immense price tag of the ground-based version. This vision represents a second phase of interstellar exploration, a generational project that could only follow a successful proof of concept from a first-generation Starshot. The lessons learned from building and operating a terrestrial laser, from hardening the nanocraft to managing the beam, would provide the essential knowledge base to attempt this even grander endeavor. It shifts the question from if we can reach the stars to how many of them we dare to approach, suggesting that our first mission to Alpha Centauri may not be an end but a brilliant beginning. The laser itself is a new kind of global commons, a tool of such power that its governance becomes inseparable from its engineering. A project of this scale cannot belong to any single flag or balance sheet. It demands a consortium unlike any before, a partnership weaving together national space agencies, private research institutions, and international scientific bodies into a unified whole. The model is not the Apollo program, a national sprint, but something more like the International Space Station, a permanent outpost built and operated by nations that were once fierce rivals. This would be its logical successor, a collaboration that extends our shared presence from low Earth orbit to the very edge of the solar system and beyond. The questions this raises are not merely technical, but deeply human. Who has the authority to aim a beam of such immense power into the heavens? Who owns the first close-up image of another world, or the spectral data hinting at an alien atmosphere? Is that data proprietary, held by the consortium that funded the mission, or is it a heritage of all humanity, released freely for every scientist and curious mind on the planet to explore? Practical logistics become matters of high diplomacy. How are launch windows allocated when thousands of probes must be deployed in precise sequence? What happens if a member nation withdraws its support or funding halfway through the decades-long project? Establishing a stable, transparent, and equitable framework to answer these questions would be a historic achievement in its own right, a dry run for how our species coordinates its actions on an interstellar stage. It forces us to confront a profound shift in identity, from nations exploring space to humanity as a whole, beginning to engage with the cosmos beyond our home system. The precedent set here could define our approach to future, even more ambitious endeavors, making the mission's legacy not just scientific, but civilizational, proving that our greatest leaps outward might first require us to learn new ways of working together right here at home. This spark of inspiration may be the mission's most profound payload. Breakthrough Starshot does more than propose a flight path to Alpha Centauri. It offers a new timeline for human ambition. For a student entering university today, the launch of such a mission could realistically occur within their professional prime. That distant point of light in the southern sky is transformed from a symbol of unattainable distance into a destination they could help reach. This shift is monumental. It replaces the abstract dream of someday with the concrete challenge of by mid-century, making careers in advanced photonics, materials science, and systems engineering not just professions but callings with a cosmic purpose. Suddenly, the complex math of relativistic physics or the meticulous design of a nanocircuit isn't merely an academic exercise. It's a direct contribution to building humanity's first starship. This generational project creates a living bridge, connecting the curiosity of a child gazing at the night sky with the tangible work of an engineer refining a laser array. It tells the next generation that the grandest adventures are not locked in history books or science fiction, but are actively being drafted in laboratories they can work in. The mission becomes a curriculum, its countless technical hurdles serving as the ultimate interdisciplinary classroom, demanding not isolated specialists, but teams who can think across the boundaries of physics, computer science, and design. This fosters what can only be called an interstellar mindset, a perspective that no longer sees the orbit of Pluto as a distant frontier, but as the inner shore of a vast ocean we are preparing to cross. Our solar system becomes a harbor, a place to build and test the vessels meant for deeper waters. The cultural ripple effect of this mindset is impossible to quantify. It encourages a long-term optimism, a belief that humanity's story is one of continued exploration and growth. It offers a unifying, aspirational goal that transcends earthly divisions, reminding us that we are, first and foremost, crew members on a single planet setting our sights on the next. While the success of the mission itself would be a triumph of engineering, its true legacy might be measured not in terabytes of data from Proxima Centauri, but in the countless young minds it inspired to look up, to study hard, and to dedicate their lives to turning the impossible into a blueprint. The greatest discovery might not be a new world, but a new generation of explorers ready to build upon it. This breathtaking synthesis is more than a blueprint. It is a new way of seeing ourselves in the cosmos. The vision of laser sailing takes the most delicate of forces, the gentle pressure of a photon, and scales it into a bridge across the stars. It is a reminder that the universe operates on principles of elegant simplicity, and that our greatest power lies not in defying those principles, but in mastering them with profound creativity. The immense challenges we face, from constructing a planetary laser to catching a whisper of data from 4 light-years away, are not walls but invitations. Each one forces a leap in human capability, spinning off technologies that will reshape our world long before the first nanocraft sails. This mission reframes the grandest of all human dreams, interstellar travel, from a vague hope for the far future into a tangible project for our century. It declares that the stars are not an inheritance we leave for our descendants, but a destination we can begin to reach within our own lifetimes. This shift in timeline is perhaps its most revolutionary gift. It transforms the work of scientists and engineers today from abstract research into the direct construction of a pathway to another sun. It tells a student studying physics or materials science that they could hold a component of the first Starship in their hands. By thinking small, by reducing a spacecraft to a silent, gram-scale wafer, we paradoxically unlock a galactic scale of ambition. We learn to build not with bulk and brute force, but with precision, patience, and an intimate understanding of light itself. As we push these boundaries, solving each intricate puzzle of the sail, the beam, and the communicator, we are doing more than engineering a probe. We are taking the first real, practical steps toward a new chapter in our story. We are learning how to carry the essence of our curiosity, our drive to explore and understand, across the profound dark between suns. The journey begins not with a roar of rockets, but with a focused, silent beam, a testament to the idea that our future among the stars may be written not in fire but in light.